minus 0.1 multiplied by 2 multiplied by 100. I didn't put it right. 100 plus 200 minus 0.1 multiplied by 2 multiplied by 100. Okay, so it will be the square root of 280. More. Okay, I want to show you another interesting thing. Okay, let's go back to a very basic example. This is, I think, 8 or 7, I forgot. Doesn't matter, 8. Let's say I take a ball and I throw it in an angle like that, in a velocity of 50 meters per second. Let's say the angle is 30 degrees, okay? This ball will obviously go something like that, reaches the ground. I want to know what will be the velocity when it reaches the ground. V final or Vt doesn't matter. And the h here is 80 meters. Now, we solved this kind of problem when we did kinematics, ballistics. You know, we divided the velocity to x and y and did all the... You remember? And if you don't, you can watch the videos again. But here I want to show you another way. Let's use this equation again. The only force applied on this object is mg, and we say we don't use it because it's already used in the potential energy. So let's use this as a reference point and say, at the beginning it has potential energy, mg multiplied by h, plus kinetic energy, mv0 squared over 2. It has the two kind of energy, height and speed, height and velocity. When it reaches the ground, it only has velocity. So we write mv final squared or vt squared over 2. Work is 0 because there is no external force on this object, only the mg, and we neglect it. Okay, very interesting because it's very, very simple. We don't have to divide the velocity to x and y, etc. Okay, let's solve it and say also one few things about the solution we get. So it's 10 multiplied by 80 plus v0 is 50 squared over 2 equals to v final squared over 2. So v final will be 800 plus 50 squared divided by, again, 800 plus 50 squared divided by 2 multiplied by 2 square root. Okay, let's write it, 64.03 meters per second. Now, this is interesting. When we solve this kind of problems in kinematics, I remind you how we solved it. We solved it like that. We found the Vx, we found the Vy, we found the final velocity in the x, final velocity in the y, and then we found the V total, okay? When we did so, this is what we got. This answer is the V final. But when we did it with kinematics, we also knew the time, we also knew the x factor here, how the range of the throwing. Here we can't find it, we can only find the total velocity it reaches the ground. Okay? So it has its advantages, it has its disadvantages. Because it's very, very short, it's an advantage, but we can't find the x, we can't find the time, so it's a little disadvantage. Okay, let's talk one more thing about this. Let's say this ball hit the ground, and this ground is from mud, okay, sticky mud, and it stops. As it reaches the ground, it stops. And I want to know how much, what happened to the energy it had. What kind of energy it had when it reaches the ground? It had only the kinetic energy, this energy. And when it stopped, obviously in the mud it's sticky, it stops, it has zero energy. Why zero? Because there is no height and no velocity when it stops. So what happened to all the energy it has? Let's calculate it for just a second. At the beginning, it had this energy. The initial energy this ball had was mgh, which is mgh plus mv squared over 2. Let's say m is 2 kilograms, okay? So it will be 2, 10, 80 plus 2, 50 squared over 2, which is 2 multiplied by 10 multiplied by 80 plus 50 squared. 4100 joules. I remind you, energy we measure with joules. This was the initial energy that this ball had. When it almost reached the ground here, all this energy, which was kinetic and potential, converted into only kinetic energy. And if you calculate it, if you do m v final squared over 2, which is 2 multiplied by 64.03 squared divided by 2, you will get exactly the same number, because the energy didn't go, it just changed. First, it had a height and velocity, potential energy and kinetic, and all these 4100 joules converted into kinetic energy. So all the 4100 joules turned into speed, to velocity. Now what happened when it reaches the ground? All these 4100 joules, they go away, because the final velocity when it reaches the ground and touches the ground, 0, it stops, no height, no velocity. So what happened to this 4100 joules? It turned into heat. If we were to use this with this equation, we would write that 4100 plus the W will be equal to 0, external W, external work. This work will be done by the friction, or if you want, by the force applied on the ball, the ground applied force on the ball. This force is, we can call it friction, we can call it the normal force, it doesn't really matter. It makes, when the ball touches the ground, it warms it a little bit. And this warmth, this energy, this 4100 joules, converted into this friction heat, or whatever you want to call it. This is the W, so the W will be minus 4100 joules. It means, again, that the ground applied work on the ball, and this work took all the energy, the kinetic and potential energy it had, and converted it into probably heat. Okay, I want to show you one more thing, a few more things, but let's start with one more thing. Okay, let's take a very simple example again, just to show you something. Okay, let's say I have a ball here, I throw it here, height is 80 meters, and let's say the velocity here is 0, and I want to find the velocity here, 50. We already did this kind of question, but I want to show you what happens if we take this as a reference point for the height. What will happen? Because usually we take this as a reference point, but if we want to take this as a reference point, how will this equation look like? The initial energy is 0 kinetic plus 0 potential. Why 0 potential energy? Gravitational potential energy. Because there is no height, I'm on the reference point. There's no height, there's no velocity. Plus, so this is the initial energy. Okay, plus the work done by external forces here is also 0, because the only force applied on this object is mg, and we said that mg is not an external force, we don't use it. So the work here is 0. When it reaches the ground, it will have kinetic energy. I'm talking 1 millimeter from the ground. Vt, let's say. But it will have also potential energy. Why? Because it has height. What is the height? It's under the reference point. So the height will be mg multiplied by minus 80. The height, if I write 80, it means I'm above my reference point, 80 meters above. If I'm under my reference point, I'll take it as a minus. So if I look at this equation another way, if I move it to this place, I'll get mg80 equals to mvt squared over 2. And it means that if I were to use the proper reference point, which is obviously this one, it means that at the beginning it had only potential energy, and all the potential energy converted into the kinetic energy at the end. And now we can solve it. M goes. 10 multiplied by 80 is V final squared over 2, so V final will be 40. Okay. Okay. Now I want to show you one more and then I'll show you. Okay, 10. Let's say I have this kind of problem. I have here a mass. Let's say velocity is 0. The height here is 20 meters. Let's say this slope is round, okay? It doesn't have to be straight line. It's round, like that. And from here, it's a straight line. There's this friction here. Friction, let's say mu kinetic equal to 0.1. Here no friction, only here the friction. And delta x here, a certain delta x here. And I say that it stops here, stops. Again, I have a mass here with no velocity. It starts moving down, there's no friction. When it reaches this point, it starts slowing down because there's friction, it slows it down, and eventually it stops. I want to know the delta x. Okay. Let's see how I use the equation again. At the beginning, we have potential energy, which is mg multiplied by 20. Obviously, this will be our reference point. And it has no kinetic energy. So this is the initial energy I have at the beginning. Now, let's see what forces are applied on this object. In this case, obviously there is the mg, there is the normal force. And in this case, there will be normal force, mg, and F kinetic. Now we don't have to, this is a very beautiful thing with energy, we don't have to divide it into parts. We can solve this problem with one equation and add all the work done, if we need to, here. So let's see. mg, we neglect it. Normal force, we don't care about it because even though the surface is round, the normal force will always be perpendicular to the distance because this is the nature of the normal force. It's always 90 degrees to the displacement. So it will not give us or take from us any energy. The work is done, will be zero from the normal force. Now, when we reach here, also mg and normal will not give us or take energy from us. The work is zero, but the friction force will take energy because the movement is here and the force is here. So it minus F kinetic multiplied by the distance it moved, which is delta x, equals to, when it reaches the ground here and it stops, there is no potential energy, there is no kinetic energy, so we write zero. Look how simple it is. W E final. Why don't we need to divide it into parts? Because energy is not something we need to divide. We can say at the beginning I have potential energy, which is this. In this part, nothing took energy and nothing gave energy. We know that what we do know is that the potential energy was converted into kinetic energy. All the potential energy here, which was with due to its height, it loses height and gains speed, velocity. So all this potential energy at the beginning was converted into kinetic energy, but the number will be the same because we didn't take anything or we didn't give anything. From this point, and this is why we don't have to find the velocity here, because we need only the energy, and the energy is the same. So I don't care if the energy comes from potential or kinetic. From this point onwards, this force took energy, so I wrote what it took, and now in the end I measure the new energy, which is 0 because it stopped. So what it happens is all the initial energy this mass had was taken due to the friction force, which means the heat applied on this with the surface is the work done by the friction force was turned into heat, okay? And the surface probably got warmed a little bit. So let's solve it. So m, which is, I don't have m 10, 20 minus F kinetic is mu kinetic multiplied by the normal force, but the normal force is mg, only here, multiplied by delta x is 0. I can wipe off the m, so 200 minus mu kinetic is 0.1, multiplied by 10, multiplied by delta x is 0. So delta x will be 200 meters. Okay, I invented these numbers, so they're a little long, okay? A little, okay, if I'm not mistaken. Okay, now I'll show you something even more interesting. Okay, we are talking about, okay, it may sound a little high at the beginning, a little complicated, but it's really very simple. Be with me. We're talking about forces which are called conservative forces. What are the conservative forces? Let's say mistakes, okay. Conservative forces. Conservative forces are forces which, when you take a route, a round route, doesn't have to be a real round route, but if I start from a certain point, I go like that, like that, like that, like that, and back, the work done by these forces is 0. So the work done by the conservative forces in a round trip, okay, you must start with the center point and reach back to certain points, is 0. This is the definition of conservative forces. I told you it sounds a little complicated, but bear with me. Suppose this is our initial point, and I just write here another point. This is A, this is B. If I go from A to B here, and I go back from B to A here, I know that total work is 0, because this was the definition. Which means that if the work done by a certain force in this direction is W, from in this direction, it means that when it goes back, it must be minus W, otherwise it will not be 0. So when it goes back. So if it goes in this direction, it must be also so if it goes in this direction, it must be plus W. So what does it mean really? It means that if I start in a certain point and I reach another point, the work done by a conservative force, it doesn't really matter which way I go. It doesn't matter if I went this way or I went this way, the work will be exactly the same. This is the meaning of this thing. A little tricky, a little complicated maybe, but the main idea is that when we use conservative forces, it doesn't really matter the way, it only matters the initial point and the final point. Now, which forces are conservative? It turns out that mg is a conservative force, and spring also is a conservative force, but we'll deal with it later. And also electric force is a conservative force. But For this lesson, we just want to know about the mg. Mg is a conservative force. It means that if I have a certain point A, let's do something like that, just to understand it, and a certain point B here, it doesn't really matter if the ball went down and up and down and up, or went straight here. If it did so, or did like that, the work will be exactly the same. So it really doesn't matter how we treat, which way it went. It only matters the initial point and the final point. How? Okay, I'll show you something easier to understand now, and how we're going to use it when we solve problems. Suppose I have a mass A here. Just to understand, let's say I did something like that. I moved it up 10 meters, I move it down 2 meters, and then I move it up 5 meters. Let's see what the mg did. The mg is this direction, okay? Obviously. So when I took it up, the work done by the mg was minus mg multiplied by 10. Why minus? Because it's opposite the direction. When I took it down, when it went down, the work done by the mg force was mg multiplied by 2, because it was with the direction. When I move it up again, it was mg multiplied by 5 minus. If I calculate them together, I'll get minus 10 plus 2 minus 8, I'll get minus 13, I think, mg multiplied by minus 13, which means that if I were to take it here, look, I got 10 here, minus this is 8 meters, and 8 plus 5 is 13. So if the ball was to go from here to there straight, or like that, and then back down, and then back up again, the work done would have been the same. So it really doesn't matter the way it did it. It just mattered where it started and when it finishes. So the conclusion really is, when we solve problems, we don't have to treat the problem, for example, this kind, and this is what we're going to do next. We don't have to find what happened from here to there, and then from here to here, and then from here to here, and then from here to here. We just go from here to here in one equation, and we get the same result. So let's show you examples, and it will be even easier to understand. So I'm 10, I think I'm 10, 11, it really doesn't matter. So now I have this roller coaster, or whatever you want to call it. Okay, let's go like that. Okay, let's say the initial height here is 100 meters. Here the height is 80 meters. And here the height here, 60 meters. And this is the ground. Okay. And I have a mass here. Velocity 0. And I have, let's say, this point is A, this is B, this is C, this is D. Let's say here I have friction. Okay, in the next example I will have friction. Here it's D, E. I want to find the velocity in each point. I want to find the VA, VB, VC, VD, VE. This is our problem. Now, and there is no friction here. When this mass starts moving, the only forces applied are mg and the normal force. Mg, we don't use it as external force because it's already in the mgh, in the potential energy. Normal, always perpendicular to the surface, to the line of movement, so it will not give energy nor take energy. So W will be 0 all the time in this kind of questions. Let's start here. The initial energy is mg 100. That's it. There's no velocity here. And if I want to know what the velocity here, I say plus W, which is 0, must be equal to mva squared over 2. And from this equation I can get the velocity in A, which is m and m goes 1000, 2000, which is VA. Okay, this is 1. 2. I want to find the VB. Now I don't need to go from here to here and then from here to here. I can go straight from here to here. This is what I'm talking about when we use conservative force. Because mg is a conservative force, we don't have to divide the way into parts. It means that at the beginning I had mg multiplied by 100, which is this energy here. I know what happened. It loses height, gain velocity, then loses velocity, gain height. But I don't really care because I write only what happened in the beginning and what in the end. There is no W here because we talked about no external forces. So when it reaches here, it will have potential energy, which is mg multiplied by AT, which is the potential energy, plus mvb squared over 2, kinetic energy. And from here I can find the kinetic energy, the velocity in B. So m goes, so 1000 equals to 800 plus VB squared over 2, so VB will be 200, 400, square root of 400, which is 20. Okay. 3. I want to find what happened to C. What is the velocity in C? Again, I don't need to go from here to here, then to here, then to here. I don't even have to solve it because the equation will be exactly the same. I'll have mg multiplied by 100, which is the initial energy, will be same as this energy, but when it's there, it only has kinetic energy. It's the same equation. So VC will be like VA, which is square root of 2000, and I already understand that it will be like the VE. It will be exactly the same as here because again it's the same problem because it really doesn't matter what it did on the way. And if I want to find what happened in D, again I write the initial energy here must be equal to the final energy here. I can, if I want, I can take it from here. I can write the energy here equals to here, or the energy here equals to here. Why doesn't it matter? Because the energy here is equal to there, to there, to there, to there. Because they are equal, it doesn't matter which is your starting point. It's easier to take it from here. So mg multiplied by 100, no W, no external W, will be equal to the energy here. Here it has height, potential energy, which is mg multiplied by 60 plus mvd squared over 2. m goes, so 1000 equals to 600 plus vd squared over 2. vd will be 400 square root of 800. Okay, this is a beautiful example to illustrate, to understand that mg is a conservative force and therefore we don't care about the path, we just want to know the initial point and the final point. Okay, more. $11. Okay, let's do another example. Okay. Let's say I have a mass here. It doesn't matter what it is. I have, this is 100 meters, this is 30 meters, and here we have friction. Oh, we don't have friction. Let's do the friction in another problem. And it's a straight line. No friction, okay? No friction. There are two questions here. Obviously, if I don't give it a push, an energy, kinetic energy, velocity, it won't climb up the mountain. So my question is, what is the V0 minimal in order for this mass to reach this point? What is the V minimal, the minimal velocity I need to give this mass in order for it to reach this point? Now we said that it only matters the initial point and the final point, but there's a barrier here. In order to reach this point, it must overcome the barrier. So what I need to ask myself, what will be the minimum velocity to overcome the barrier? In other words, to reach here in the velocity of 0. If it reaches here in the velocity 0, what will happen? 0.0001, but we just say 0. From here, it will just slide down, loses potential energy, then go up a little, and reach this point automatically. So we need to ask ourselves what velocity to give it here in order for it to reach this point. So we'll do it again. mv0 squared over 2, which is the initial energy. No external work, because the only forces applied here are mg and normal force, and we talked about them. So all this kinetic energy, I want to convert it into mg 100. Potential energy, because I want it to reach here with the velocity 0. Of course, if I give it more push, it will reach here with a certain velocity, and it obviously will continue. But I want the minimum I need. Okay, so I'll get the V0 squared equals to 2000. So V0 is square root of 2000. Now, once I gave it this velocity, it will reach here, and I want to know what will be the velocity here. Now, it doesn't really matter if I measure it from here, if I start from there, because I know it's going to reach there. So let's start it from here. I'll write mv0 squared over 2 will be equal to the energy here, and the energy here will be mg30, which is the potential energy, plus mv final squared over 2, or vt squared, doesn't matter. Okay? Because now I know when I give it this speed, it will overcome this barrier and reach here. It's on the edge. Yes, I need to give it maybe a little more, but it's okay. So m goes. V squared is 2000 over 2 equals to 300 plus mv5 over 2. So 1700, 1400 square root. It means that if I gave it this amount of velocity, it will reach here, and the velocity of this, if I'm not mistaken. Okay, one more. Now let's do with something with friction. Well, okay, suppose I have this problem. Okay, initial height is 80 meters. I have a mass here, and this height is 20 meters, and only here I have friction, which is, let's say the distance here is 40 meters, from here to there, and the friction force is, the coefficient is 0.2, and it stops exactly here. And the question is, no, let's leave D open, okay? D equals to, let's ask what the distance is. I'm talking about a mass here. It starts with the velocity 0, let's say. Obviously, what will happen to it? It will gain speed, lose height, then gain height, lose a little speed, then gain speed again, then lose speed again. Why it must reach here? Because unless there is a barrier, just look at this. If we start here with a 0 velocity, it means that it has a certain amount of potential energy. Let's say 100 joules, for example. This 100 joules, what's going to happen now? It's going to gain velocity, lose height, but it will still have the 100 joules because there is no friction. There is no external force that took something. So it will lose height, gain velocity. When it reaches here, it will have also the 100 joules, but instead of height, they will be interpreted into speed. Now when it reaches, go back up again, it loses speed, still 100 joules remained, and it gains height. When it reaches exactly the same height, all the 100 joules will be transferred also, all will be transferred, converted into the same height, and it will stop. It can't reach more than that, because if it were to go higher, it means that it must have more than 100 joules, but it didn't, it only had 100. So it will go exactly to the same height if there is no friction. If there is friction, the friction took a little bit, so for example, if the friction is 10 joules, so it will have in the end only 90 joules. 90 joules, it means that the height must be a little somewhere lower. What I want to talk, why did I show you that? Because look at these heights. These heights are lower than the initial height, and there is no friction here, only here. So it means that if it has certain energy here, it will lose height, gain speed, lose speed, gain height, but it will manage to go here. It won't manage to go if the height is bigger than 80 meters, but it's not. So I don't really care about these. I only care at the beginning, at the end. So let's write our equation. At the beginning we had no kinetic energy, only potential energy, mg multiplied by 80. Okay, that's the initial energy. The work done, all this up until here, there is zero work because there is no friction. Normal force does nothing. Mg is already taken when we use the MGH. When we write mg80, it means that we already used this mg. Okay, so there is no external work here, but here it's an external work. Because here we have the normal, obviously, the mg, but we have the friction force, the kinetic friction force. Okay, so we write minus Fk multiplied by d. It's minus because it's against the line of movement. It stops. When it stops, so this was the W. When it stops, it has no kinetic energy, zero kinetic, but it still has potential energy. So it will have mg multiplied by 20. Okay? The kinetic force, I remind you, it's mu kinetic multiplied by the normal, which is mg. So our equation will be m goes, so it's 10 multiplied by 80 minus mu kinetic is 0.2. 0.2 multiplied by 10 multiplied by d equals to 10 multiplied by 20. So from here we can find d. D will be, this is 800, this is 200. So it's 600 divided by 2, I think. I don't need calculator. 600 divided by 2, 300 meters. Okay, a little long. It's okay. 800, 600. Okay, because I invented it, and when I invent it, automatically I don't really think about the numbers. It's okay. Okay, I think this is the idea. I think I showed you how to approach these kind of problems. Should we do one more? I'm thinking. Instinctively, I say no, but there's a question here in my mind. It's a nice question to solve. Let me think. Okay, just one more. Okay, let's say I have two slopes. Let's say this is 45 degrees. This is also 45 degrees. I have a mass here. It's a little round here. It goes here. It goes here, and I have here an h, a certain h. Okay, and I say the mu here is mu kinetic, which is mu, And the mu here is 2 mu's. Okay? 2 mu. So there is a friction force, mu and 2 mu. And I know the mass reaches here and stops. Stops. And the h here is little h. It's a little... sorry, just a minute. Okay. And I want to know what is the ratio between h and small h. This is the question. A little advanced, but still we can solve it. This problem we can solve in 2 different ways. In kinematics, we find forces, acceleration, it's heavy. Or we can use the conservation of energy and solve it. And we'll do so. What are the forces applied here? Obviously mg, normal force and friction force here. Let's call it Fk1. Here, it's also mg, also normal force, and let's call it Fk2. Okay, when we break the mg, we'll get mg cosine 45 and mg sine 45. When we break it here, we'll get also mg cosine 45 and mg sine 45. Okay. Now let's see how I solve this problem in one equation. I don't need to find velocities and kinematics, which is a long way to solve it. This is a isosceles. If this is h, this is also h, and this is square root of 2h according to the Pythagorean theorem. This is also h, this will be h also, so this will be also square root of 2h. Okay, so let's write our equation. At the beginning it has no kinetic energy, only potential energy, which is mgh. Okay, when it moved here and there, the forces applied on it were friction, mg, and normal. Here, normal and mg we don't use them, only the friction force. Obviously they took energy. So this force took Fk1 multiplied by the way it went, which is this way. This was the displacement for the Fk1. Minus, this one also took something. What did it took? The Fak2 multiplied by the way here, by the distance here, which is square root of 2 small h. And when it reaches here, it stopped. When it stopped, there's also no kinetic energy, only potential energy, which is mgh. This is our equation. Again, this was the initial energy. This was the work done by the external forces, which are the friction here and the friction here, both the frictions. This friction was in this way, this friction used this way, and this is the E final, only potential. Okay, let's see what we can do. mgh minus, instead of Fk1 I can write mu multiplied by the normal, which is mg cosine 45, multiplied by that, minus Fk2 is 2 mu's, because, okay, multiplied by the normal, which is again mg cosine 45, multiplied by square root of 2h, and this will be equal to mgh. Okay, now I can wipe off the mg, and I can write h minus, okay, cosine 45 is that. When we multiply it by that, I'll get 1. So this is 1. Again, cosine 45 in the calculator is this multiplied by that is 1. You can check it. I'll check it. Cosine 45 multiplied by square root of 2 is 1. I didn't really write it, I just did a show for you. Okay, so minus mu multiplied by h minus, again, this is 1. I can do another show, but I won't. Okay, 2 small h equals to small h. 2 mu's, forgot the mu. Mu h. I hope I'm right. Again, h minus mu multiplied by h minus 2 mu multiplied by small h equals to h. Okay, so h1 minus mu equals to h1 plus 2 mu. So h divided by h will be 1 plus 2 mu's divided by 1 minus mu. Okay. Okay. So I found it. Okay. Okay, it's a very beautiful question to understand how to use this equation. The math is a little higher here because there's no numbers, only letters, but the idea is the same. Initial energy minus all, or minus or plus all the work done by the forces equals to the final energy. In this case, it means that all the height here, first of all, the height at the beginning must be higher than the height in the end, because in the beginning I had a lot of energy, the mgh. The frictions took something, and in the end I am left only with that. One other thing, okay, we leave it like that. There are many questions I can still ask about this problem, but it's fine. Okay, so this is the basis of energy, potential energy, kinetic energy, work, and our next lesson we'll do something nice. So we'll have to be patient and see. Okay, thanks.